We will discuss another problem. Here, this draw SFD and BMD of following beam subjected to point load of 20 kN and then a UDL of intensity 10 kN per meter, UVL of 60 kN per meter, and there is a load. It is not actually working at point E, it is just at a distance of 0.5 meter and acting at a certain height, right? And then here it is hinge supported at point B, right? The new thing in this problem is a combination of loading is acting on here. In previous lecture, whatever we had discussed, there is either it's case of UDL or UVL or point load, but here we are finding everything in this problem. This section is solely a different, right? Here load is not acting at point E, but it is at a height, at a certain height and a distance 0.5 from point E, and magnitude of this load is 30 kN. So whenever such a problem will face, we require to transfer this force from this place to point A, and theorem that we use is known as transfer of forces from parallel position, right? So for doing this, what we do, let make a clear picture. This is exactly a 30 kN and this is point A, right? So make a two equal and opposite load at point E, 30 kN and it will be 30 kN, right? And this situation, these addition of these two loads will not affect the equilibrium condition of the beam because they both are cancelling each other, right? Now what we see, this 30 kN and this 30 kN, they both are parallel to each other. They both are parallel to each other and equal in magnitude. We can say these two forces can form a couple, right? If we eliminate these two forces by a couple, then there will be at point E there will be a force 30 kN and a magnitude of a couple 30 into 0.5 equal to 15 kN meter. So whenever you are going to transfer a force parallelly to another place, then it will be transferred by magnitude of the force itself and then a moment of this force about this point. 30 into 0.5 is moment, it is rotating in clockwise direction. So here we have shown the direction of couple in anti-clockwise direction. Oh, it is clockwise direction because this force is rotating the system about E in clockwise direction, right? So system can be now replaced in this way. Now we have, this is point A, this is point C, this is A, this is B, this is E, and this is D. At point E, now force is parallelly transferred by its magnitude and the moment 15 kN meter, right? Now we have to calculate the reaction at A and B. Already it is mentioned, but we are going to calculate it. This is here, already we have shown the answer. This is your RA and this is RB, right? Find the value of RA and RB. if we apply sigma Fy equal to 0, then it will be Ra plus Rv equal to 20 plus this is of 10 kilonewton per meter plus 20. Total weight of UVL is 60 into 6 upon 2 plus 30. Right? It will be equal to, this one will be equal to 180, 210 and 250. Now take moment about B, then moment will be 20 into 6 to 8 to 10 into 12 anticlockwise will rotate the system about point B in anticlockwise direction, minus 20 into 12 minus, then total weight of udel is 10 into 2, it will act at half of 2, then it is 1 and distance from B will be 1 plus 6 7 to 9 to 11, then minus 20 into 11. Now moment of Ra about B, it will be Ra into 10. Then moment of total weight of UVL about B, total weight of UVL is 180 kilonewton. It is acting at 3 from its maximum intensity line, right? Total weight of UVL is at 1/3 of distance from its maximum intensity line, so it will be L by 3, L is 6, 6 by 3 is 2, so 2 plus 2 plus 2, it is 6, right? So then it will be minus 180 into 6. Now moment of 30 kilonewton about B, it will be minus 30 into 2. And another exactly a moment is given 15 kilonewton meter of magnitude of this moment is 15 kilonewton meter, and it is in clockwise direction, and during the calculation of reaction we consider clockwise rotation of moment positive, then it is plus 15 equal to 0. When we solve it, we will find R equal to, it will be the R equal to 158.5 kilonewton, and put this value in equation 1 here, then value will be RV equal to 91.5 kilonewton. 91.5 kilonewton. So reactions are known now, RA and RB. Now we will go to the calculation of the problem. Here it can be shown like this way. When RA and RB is known, we take the previous problem. Here, now you can mention RA is 158.5 and RB is 91.5. Now we'll go through second step. We have to calculate shear force value for each section and then for each point, right? We are moving from left to right. Then we will start from the portion CA, then AD, then we will move to DE and then EV. For each section, we will calculate shear force and bending moment value. Right? Already I have made a diagram of here, 12 forces, right? So now consider first section CA. Consider first section CA. If you see in this diagram, then CA will be here, and distance will be x. So I have made it here. This is CA. When we take CA, when we are considering A, then it section will be just left of A, right? Section will be just left of A. Then there, in the diagram of section of the beam, there will be no point A, right? If we make the shear force equation for this section beam, then Fx equal to will come minus 20 minus 10x, right? For this x length of UDL, there is a 20 kilonewton of point load, and there is UDL of 10 kilonewton per meter intensity for x length, right? The total weight of UDL will be 10x. It acts in downward direction. So by sign convention of shear force, for the left segment, it is minus 20 minus 10x. Clear? Now, calculate the value for each load points. Then for C, x equal to 0 and FC will be minus 20. For A, x equal to 2 meter, FA equal to minus 40, right? Now, value is known for C and A. We will calculate for the same portion bending moment value. When we will calculate bending moment value, then we have to take the moment of all forces about the section. Then what we are seeing that 20 kilonewton is at a distance of x, then moment of this force about section is minus 20x. Already we have studied that from sign convention, for all downward forces, bending moment value is negative, right? Then minus 20x, total weight of UDL is 10x. It act at half of x, so total weight of UDL is 10x, and this 10x is at x by 2 from the section. So moment of this 10x is 10x into x by 2, right? Here, in this case, x ki power n, x in the power of x is 1, then variation will be linear. And here, the power of x is 2, then variation will be parabolic, right? So, for at C, as C is the start point, then moment will be 0 for x equal to 0, and for x equal to 2, put the value of x here, then it will be minus 20 into 2 minus 10 into 2 into 2 upon 2, then value will be minus 40, and minus 20, it is minus 60, m equal to minus 60, right? The portion C is completed. We have calculated the value of shear force and bending moment value for portion CA. Now come to the portion AD, right? Portion AD, when we are considering portion AD, then section will be just left of D, right? Write the equation for this portion. Shear force equation will be minus 20. It is in downward direction, so it is minus. Then total length of UDL is here. Total weight of UDL is minus 20. And then reaction plus 158.5. And then total weight of UDL. Already we have covered it in previous lecture. Total weight of section UVL, total weight of section UVL is Wx square upon 2L. So W is given 60 kilonewton per meter, 60x square upon 2L. L is the length of UVL. Length of UVL is given 6. Variation is parabolic because power of x is 2. For x equal to 0, f A equal to minus 40 plus 158.5 minus 40 plus 158.5, it will be equal to 1 18.5 kilonewton. If we mention the unit here, then there is no need to write unit again and again. Then Fa, it will be 118.5, and for x equal to 6, Fd equal to, put the value 6 at place of x, then Fd will be minus 61.5. Now what we are finding, at point A, value of shear force is positive, and at point D, value of shear force is negative, right? That suggests variation changes its sign in between this portion. For portion AD, A value of shear force is positive, and at point D value is negative. That means in between these 2 points, shear force curve changes its signs. That means the value of shear force is being 0 in somewhere else. So we will calculate 0 shear force point, because value of shear force at a given point, at a start point is positive and in second point is negative, then obviously there will be a 0 shear force point. So we will make a calculation for 0 shear force point. For 0 shear force point, Fx equal to 0. So make this equation 0, minus 40 plus 158.5 minus 60x square upon 2 into 6 equal to 0. When we calculate, we will find x equal to 4.86 meter. This value showing that at a distance from A, at distance 4.86 meter from point A, value of shear force is being 0, or shear force curve changes its sign. It is moving from positive area to negative region, right? Now calculate bending moment value for this section. Mention unit here, it is kilonewton meter. Then mx will be, for this section, mx will be, take the moment of this force about this section, what will be it? It is minus 20 into 2 plus x. Now take the moment of this total weight of udil, that is 20. It is acting at 1 meter from point A. Then total distance from the section will be 1 plus x, then minus 20 into 1 plus x. Moment of this reaction force will be plus 158.5 into x. And already we have studied that moment of section, your bending moment value for section UL is Wx cube upon 6L. It is in downward direction, then it will be negative, and WH given 60, x cube upon 6, length of UL is 6, power of x is 3, then variation will be of cubic nature. I mentioned it by C, right? Now calculate value for each point. Load points are A and D. For A, value of x is 0, and x equal to 0. Put the value of x 0 here. Then we'll find MA equal to minus 60. MA equal to minus 60, but this term will be 0, this term will be 0, here will be minus 20, here will be minus 40, then it is minus 60. And for x equal to 6, there will be point D, MD equal to minus, MD equal to, sorry, it will not be minus 12, it will be 291 kilonewton meter. Put the value x here, place the value x equal to 6, then it's 6 to 8 minus 160, then 6 plus 1 is minus 140, it is minus 300, right? Here it will be minus 360, minus 660, and 158.5 into 6, subtract this 660 value from this one, then we will find 291 kilonewton meter. Now for this portion, shear force is being 0, right, at x equal to 4.86 meter, then we will calculate maximum BM value, M max. If we make a boundary, then mx will be at x equal to 4.86, then value will be minus 20 into 6.86, 20 into 6.86 minus 20 into 5.86 plus 158.5 into 4.86 minus 60 into 4.86 cube upon 36. Then this value will be, when we calculate, we will find maximum bending moment value is 331.59 kilonewton meter, right? So at this zero shear force point, bending moment value is maximum. Now here at point A, bending moment value is negative, and at point D, bending moment value is positive. That means bending moment curve changing its sign between these 2 points. So we will calculate zero bending moment point for this section, and that is known as point of contraflexure. What is point of contraflexure? This is the point at which BM curve changes its sign. Right? So bending moment curve, mx will be 0 here. Make this equation equal to 0. 0.5 into x minus 60x cube upon 6 into 6 equal to 0. Solve this equation, then we will find the value. There will be 2 values for this expression, and these 2 values are x equal to 0.51 meter, and second will be 70.59 meter. So this is not a correct value, this is incorrect value, because value must be less than 6, right? Why? The length of portion AD is 6 meter. Length of portion AD is 6 meter. So this one will be correct. This is our suitable value, correct value. The x equal to 0.51 meter. This will be a point of contraflexure for portion AD, right? Now move for the next portion. Next portion is DE. Next portion is DE. Write the equation for portion DE. This is the loading diagram for portion DE. Then question is 20 minus 20 minus 20 plus 158.5 minus 180, right? And this is equal to minus 61.5. It is independent of x, then value for both point will be minus 61.5, and variation will be constant line. Now calculate bending moment value. Mx will be here. Mx for this portion will be minus 20 into 8 plus x minus 20 into 7 plus x plus 158.5 into 6 plus x. And now total weight of udel is 180 and it is at distance D, it is at distance of 2 meter from D, and from section it will be 2 plus x. Then equation can be written as minus 180 into 2 plus x. For x equal to 0, there will be point D and MD will be equal to 291, and for x equal to 2 meter, it will be point E, and value for this point is 168. Right? Put the value of x into this equation, we'll find the value 168. Right? Variation. Here is constant line. Obviously, there will be power of x. Power of x is here 1. So variation will be inclined line or linear one. Right? Now next portion is EB. Loading diagram for EB will be like this way, just left off. We will take a section. Oh no, this point load and this 15 kilonewton meter couple is included in the loading diagram. Shear force, write shear force equation for this portion. Then it will be Fx equal to minus 20 minus magnitude is 10 kilonewton meter minus 20 plus 158.5, and total weight of udel is minus 180, and this one is given minus 30. Right? The total value is minus, because this value is already calculated, this is equal to minus 61.5. 30 is being added here. This total value is minus 91.5. This value is again independent of x. Then for x equal to 0 and for x equal to 2, at both point Fe will be equal to Fb, and this is equal to minus 91.5. Now write the equation for bending moment. Mx will be minus 20. Distance is 6 plus 2 plus 2, 10. X2 8 plus 2, 10. Minus 20 into 10 plus x. Minus 20. This distance is total weight of udel is at distance 1 meter from A. Then it will be minus 20 into 9 plus x. Minus, it will be plus because it's in upward force. Then bending moment upward force is positive. Then 158.5 into 6 plus 2, 8 plus x. Total of weight of udel is 180. 180 into this distance is 2. 2 plus 2, 4 plus x. And then there is a moment. Moment of 15 kilonewton meter. It is of clockwise direction. Right? So when for left segment, clockwise rotation of rotation is considered positive, then it will be taken positive plus 15, and next take the moment of this 30 kilonewton about the section, this downward direction, then minus 30 into 2. For x equal to 0, there will be point E, ME. Put the value of x0 here, then value here will be 183 kilonewton meter, and for point B it will be 0, as already we have discussed. For start and end point of beam, bending moment value is always 0 until and unless an external moment is not given. If external moment is not given from start for start and end point, then at both point bending moment value will be 0. Now the analysis of each portion is completed. We will make a summary of these portions. We will make summary of shear force and bending moment value for all the portions. Here already I have tabulated them. When we are considering section CA, then we have find the value of shear force at point A, FA equal to, FC equal to, at point C, minus 20, and for point A it is minus 40, right? Sign of these shear force value for these two load points is same, so there will be no zero shear force point, right? Similarly, bending moment value recorded for these two points, MC equal to 0 and MA equal to minus 60, and sign is same, then there will be no point of controflexure. Now for portion AD, shear force value at point A is 118.5 positive, and at D it is minus 61.5. So here there are opposite signs. At point A shear force is positive and point D negative, then there obviously there will be a zero shear force point, yes, and it is at x equal to 4.86 meter from A. Now calculate bending moment value. MA equal to minus 60, and at D equal to 291, and maximum value at zero shear force point Ax equal to 4.86, M max is 331.59. Obviously there will be point of contraflexure because bending moment value at point A is negative and at point D is positive, right? So point of contraflexure that we have calculated it is x equal to 0.51 meter from A. So this portion is now completed. For portion D, shear force recorded is FD equal to minus 61.5, and at E it is minus 61.5. Sign are same, then there will be no zero shear force point, and T equal to 291, and bending moment value at E is 168 kilonewton meter. Signs are same, then there will be no point of contraflexure, right? For portion EB, F is minus 91.5, and for portion FB is minus 91.5. Signs are same, there will be no zero shear force point. And for portion B, and bending moment value for this portion, MA is 183 kilonewton meter, and for portion, for point B, MB will be 0. At a start point, say bending moment is 0, at end point bending moment is 0. Signs are same, there will be no point of contraflexure. There is one observing point. At E, an external moment is given. So what will be the effect of this external moment in bending moment? What is the effect? There are two values. When we are considering this external moment, when we are not considering this external moment, the value of bending moment at this point is 168. And when we are considering this external moment, value of bending moment at this point is 183. Right? So there are two bending moment value. Without considering external effect, it is 168, and with the external effect, with the external moment, it is 183, right? Now we will draw with the help of this summary sheet the shear force and bending moment curve for this problem, right? this is our length of the beam. This is point C. For point C, value is minus 20. Then at point A, this is minus 40. Udil here, power of x for this is 1. Then there will be a linear relation 20, 40. At point A, it is 118. Point 5, and at D it is 61.5, and this portion is subjected to UVL. Power of x is 2. Already we have covered it. Then there will be a parabolic variation. This will be drawn like this way. Variation is parabolic. And shear force is being 0. At this point already we have calculated where it is being 0. It is being 0 at Ax equal to 4.86 meter. 4.86. Right? Now at D, value is for portion D, and value is minus 61.5. For A it is 61.5. Here for portion D there is point load, so it is constant. At E value is 61.5. Now at E it is 91.5. 30 is added here, so this will come here this way, and here the value is 91.5. and at B it is 91.5. From D to B there is point load, then there will be a constant line. Already it is mentioned during the analysis previous pages. So it is 91.5. Close the curve. So this is required shear force diagram for this case, right? Now draw bending moment diagram for this portion. At C value is 0. At A, at C value is 0. At A minus 60. Here I have shown minus 60. Variation will be just power of x. Power of x in shear force is 1. Then in that portion power of x will be 2. Just one digit ahead, one power ahead. So already it is discussed. We have seen it in general equation. When we have made the general equation in this one, then in this case it was 10 in x into x by 2, 10x square. So variation is parabolic. Then we will draw a parabolic derivation between them, 60. You can see now in previous portion when we have drawn a parabolic variation like here, then it is upside, right? When it move downside of this reference line, it will come inside. Curve is always inside, right? What I'm saying, it cannot be like this way. Suppose here is point 0 A and value is 0, and here point B and value is 60, and variation is parabolic, then you will not draw like this way, right? It will be, for this case, like this one. This is inside, right? So that means this one is wrong and this one is right way to represent parabolic variation. So I have seen it like this way. Now at C it is 0, at A it is 0. Now move to for another portion. At A value is 60, at D is 291. Now value is 291. Here is, I'm considering this value is 291, right? And at A it is minus 60, at D it is 291, and maximum value is 331.59 at X equal to 4.86. Then we will make here dotted line from X equal to 4.86 and say this is value 331.59, and variation will be, here it is parabolic, then it will 1 power ahead, variation will be cubic 1, and draw cubic variation. You start from this point, it will move to here, then it will come to down like this way. This is the maximum value of bending moment, 331.59. Now what we are finding that this curvature is moving from negative region to positive region at this point, right? At this point, so distance of this point from point A, distance of this point from point A is 0.51, that is point of contraflexure. Here we have mentioned it, this is X equal to 0.51. So this is your point of contraflexure, because at this point bending moment curve is changing its sign. This is point of contraflexure, right? BC point, and this distance is 0.51 meter. Now at this point, move to other portion. Next portion is DE. For D, value is 291. Okay, this is 291, and for E it is 168. Now here at E, value is 168 for portion D, and this is constant line. Then obviously it will be inclined line. 1 power ahead. Here x here the power of x is 0. Then it will be power of x will be here 1. That is an inclined line, 168. Now for the last portion EB, the value of bending moment at E is 183, right? Obviously this portion already we have discussed that this there is two value for point E, 168 and 183, due to the external moment added on this portion. So previously it is 168. When external moment is added, external moment amount is 15, then this value is 183. Add 15 added here. 183 from point D to this height is 183, and from point D to this height is 168, right? Okay, from point D to up to this point is 168. Now we'll measure 183 from here, then this one, and difference of 183 and 168 is 15. This is showing that at this point external moment is added, right? So 183 at end of the beam, at end point of the beam, bending moment is 0. Here variation is constant line, then bending moment variation will be inclined line. Power of x will be 1 ahead, right? So this is the required bending moment diagram, and this is required shear force diagram for this given problem.